Hello everyone and welcome to Freeze-Drying Process Analytical Technology using Heat Flux Measurement, presented by American Pharmaceutical Review and sponsored by Millrock Technology. My name is John Essex, Editor-in-Chief of American Pharmaceutical Review, and I will be your moderator. Before we begin, I'd like to inform our viewers that this event will hold a live question and answer session at the end of the presentation. You can submit a question at any time using the Q&A box on your screen. Now allow me to introduce today's presenter. Mr. T.N. Thompson is president of Millrock Technology, a manufacturer of high-tech freeze dryers. Millrock Technology focuses on improving freeze-drying equipment and control systems and has developed several recent patents for new technologies. Mr. Thompson was previously the president of FTS Systems. It is my pleasure to welcome Mr. Thompson.
Good afternoon, morning or evening, depending on where you are. I see that we have attendees from really all over the world. Today I'm going to be talking a little bit about a new technology that we're working with here, where we're using heat flux to monitor and control the freeze-drying process. We refer to that as LyoPat. Heat flux measurement as a process analytical technology can be used to measure all sorts of neat things during the process. And one of the nice things about it is it's in situ during the entire process. It's continuous, it's real time, non-invasive, non-interrupting, is batch size independent. You could use it for single vials if you wanted to. Works a little bit better with more than a single vial, but certainly can give you some neat information. But one of the key things is that it works for the entire freeze-drying process. That includes the freezing process, the primary drying process, and the secondary drying process. In addition, it's freeze-dryer independent, so it doesn't necessarily have to be on any specific type of freeze-dryer. First, some key things that we need to understand so that when we look at the actual runs and information that we'll be presenting, they make more sense. The first concept is temperature versus heat flow. Let's start with the freezing process. During the freezing process where the ice crystals are forming, the temperature of the product once the product is nucleated doesn't change, but the heat flow will change dramatically. That heat flow is one of the things that we measure and look at and can control. And we're going to see what the impact of controlling that heat flow has on the primary drying process. Now, during primary drying, you have a slightly different effect where the dry layer increases and your sublimation rate changes. And depending on how the product was frozen, we can actually see the heat flow change over time. You'll see that in some cases the heat flow doesn't change much at all, or in some cases it changes pretty dramatically. If we look at some of the more common, what are referred to as P80 techniques, you'll notice that most of those really only work in the primary drying process. Thermocouples, capacitance manometer versus Pirani for endpoint determination, pressurized testing for determining product temperature during the primary drying phase, MTM, T-Day LAS. The only one of the techniques that actually works for the entire process would be a heat flow measurement. The heat flow measurement that we do uses a heat flux sensor that's placed between the shelf and the vials so that we can actually measure the amount of heat coming from the shelf into the vials, or vice versa, depending on whether you're heating or cooling the process. Now, what we can do with this is if we add a thermocouple to the process in the vial, and we can add a thermocouple to the shelf, we can actually calculate the thermal conductivity of the vial, or actually should say measure it, because we have the heat flow. If you look down here in the if you look down in the lower right-hand side, you can actually see the equation. It's a very small equation there where kV equals the heat flux over the temperature of the shelf minus the temperature of the product, and that's times the area. So we can actually determine what the kV of the process is. One of the things we're also going to look at is kV is considered a constant, and depending on how you're measuring that, you want to make sure that you're measuring kV during the initial portion of the primary drawing cycle. So if we can measure the heat flow going into the vials, we can also determine the thermal conductivity of the vial, the heat transfer coefficient. We can calculate the product temperature based on that. We can also calculate the mass transfer going on per vial and per batch, determine the product resistance, and ultimately predict the primary drawing cycle time. Now, some of the neat events that you can actually see during the process, which aren't necessarily measurements, but we can actually tell when the product has supercooled and is ready for nucleation because the heat flow approaches zero. You can look at the nucleation event. We can determine when the end of freezing is done, and I'll explain a little bit more about that in a minute. The end of primary drawing, because the heat flow is going to go basically to zero. And we can tell changes in performance. I'll have an example in here where we've actually saw a collapse of a material that was close to the heat flow sensor. The technologies that we used in some of the testing that we're going to present here are first what we call AccuFlux, which is the heat flux sensor between the vials and the shelf. And we're also going to compare different freezing methods, including controlled nucleation. In this case, we used what we call freeze booster, which is our technique for injecting ice fog. And the combination of those allows us to perform multiple cycles or multiple different configurations to determine the effect on the actual product. We call the combination LyoPat. This is an example of what we call a nucleation station, which is used for performing the nucleation event. It is an ice fog injection system. Typically, it's placed on the front door of any freeze dryer, and through a set of different parameters, can be used to actually nucleate the product. Great for laboratory testing to see what the effect of controlled nucleation is. The beauty of this particular technique is that you can put a door on each of your freeze dryers and use one nucleation station across your entire lot of freeze dryers. And they'll be available in multiple sizes as well for larger systems and steam sterilizable systems. So, one more thing that we need to understand is we're going to be talking a lot about the freezing process and how that affects the primary drying process. So we have to understand what the actual freezing process is. And freezing actually is three unique events. The first is nucleation. Nucleation is the initial formation of ice crystals in the available water. Not commonly understood that when nucleation occurs, it's basically absorbing the energy that's available, and it raises the temperature of the product or the water until no more nucleation can take place, or no more ice crystal can take place. Ice crystal growth can take place, that is. So if you do some steady state calculations, somewhere between 3 and 19% of the available water actually forms ice crystals during the nucleation event. In most of the experiments that we've performed, is somewhere actually between 7 and 10% of the initial ice crystal growth takes place during nucleation. Once you're finished with the nucleation, then you have the crystallization of the equilibrium freeze concentrate. That means that somewhere between 93 and 85% of the ice crystal growth takes place after nucleation and over a fairly long period of time. This crystallization of the equilibrium freeze concentrate could take 1 or 2 hours, depending on what your freeze method is. That's important because during that period of time, your heat flow is going to change fairly dramatically. The last portion of freezing is once your available water has crystallized, you have the maximal freeze concentrate, which then solidifies. We're going to run 4 different freezing profiles, and we're going to look at the effect of those on the primary drying process. Those 4 are simple ramp, The second one's going to be a hold and a ramp. Third one will be controlled nucleation with a ramp. And the last one will be controlled nucleation and then controlled heat flow for the post-nucleation ice crystal growth. This is where the rubber meets the road, as they say. If you take a look at this graph, this is the typical freezing cycle that somebody might use, where we're reducing the shelf temperature from 20 degrees to minus 40 degrees at half a degree C per minute. So if you look at the gray and yellow lines, that is the shelf set point and the shelf temperature at the shelf inlet, and the typical profile at half a degree C per minute. The blue line is the temperature of the surface of the shelf. The green line is the average temperature of the product, and you'll notice that about halfway into the freezing process, the temperature average stays somewhere just below 0 degrees. The key there is that during that process, the temperature of the product's not changing. However, that's where your ice crystal formation is taking place. The red line is the heat flow that takes place during the freezing process. There are some significant events that take place here. So as the shelf is cooled down and your product starts to cool down, you start to get nucleation events. You'll notice here that this sensor measured 3 different nucleation events taking place at different times and different temperatures during the freezing process. The heat flow during the freezing process takes this V-shaped pattern. It increases pretty dramatically, or it goes from 0 toward minus 2,000 watts per square meter, and then comes back up towards 0 as the ice crystal formation completes and your product is reaching stability. The depth of this V-shape means that you have the deeper it is, the smaller the ice crystal that's created. All right? We're going to look at that because the smaller the ice crystal that's created, the longer the freeze drying or primary drying cycle is going to take. So again, here's a standard cycle, 3 nucleation events, and the change in heat flow that takes place during the standard freezing cycle. You'll notice that during standard freezing, it's a bottom-up nucleation event, which means that it starts at the bottom of the vial, ends up at the top. Now, because we have a very large, we have heterogeneous nucleation, and we have a very large change in heat flow, we not only have a non-uniformity across the batch, but also in the vial. So we're not creating a very porous structure for freeze drying. For the second freezing method that we did, is we took the shelf down to minus 5 and allowed the product to stabilize at minus 5, and then ramped it down to minus 40 at half a degree C per minute. You'll notice that the heat flow has a pretty large spike in it, and we didn't intend to create a nucleation event, but one of the vials randomly nucleated even at minus 5 degrees. Now, we're not in a super sterile location here, so probably a little higher particulate content than in most laboratories. But the interesting part about that was, even though we were holding at minus 5, is we did have a nucleation event on one of the vials at or near the heat flux sensor in this case. Now, once we allowed the batch of vials to stabilize at minus 5, we then started to reduce the shelf temperature. And so we held the shelf at minus 5 up until 110 minutes into the run, started to decrease the shelf temperature. And again, you'll notice that we had some significant nucleation events that took place, and the heat flow, again, has this V-shaped pattern. However, it's not quite as deep as the previous one. You'll notice that in this particular slide, we went to about minus 1,500 watts per square meter on the heat flux. In the previous one, it was about minus 2,000. So theoretically, we should have a little bit better, a little more porous crystal structure going on here. Because this is, again, not controlled nucleation, it was bottom-up freezing, pretty random nucleation still, so the uniformity across the batch is still in question, and the uniformity in the vial is still in question. The third freezing profile that we ran was a controlled nucleation event. The controlled nucleation event in this case was we brought the shelf, by the way, did not mention, which is probably the question running through your head is, what's the product that we're running here? We're running a 5% sucrose, 3 mil fill in a 10 mil vial, and that's what we've done for all the experiments that you'll be looking at. So here we took the temperature of the shelf down to -5. We allowed the product to stabilize so the heat flow comes up towards 0. And then we created the nucleation event using our freeze booster controlled nucleation technology. And that nucleates all of the vials at the same time. Once nucleated, we then reduce the shelf temperature to -40 at half a degree C per minute. By the way, the nice part about controlled nucleation is we've now created a uniform starting point across the batch. Everything was basically initialized at the same time and same temperature, so we should have a nice starting point. However, we still have this huge, well, relatively huge heat flow change during the equilibrium freeze concentrate freezing. Again, you'll notice it's a lower number than the previous slide. We're now at about -950 watts per square meter. So we should have a more porous structure than the previous 2 freezing cycles. Now, another important point to remember that when you're using a controlled nucleation process, the freezing starts at the top of the vial and irradiates down. Now, it radiates down, however, the shelf is actually creating the cooling, so we find that it kind of meets itself in the middle, so you'll get it both from the top and the bottom of the vial. But because we just did a ramp after controlled nucleation, we still don't have the most uniform structure inside the vial. The fourth freezing method that we used was controlled nucleation. Again, same as the previous slide, we took the vials to -5, allowed them to stabilize, so you can see the heat flow drops and then comes back up towards 0. Once stable, we don't have to wait for any other information. We say, okay, we're within 30 watts per square meter of 0. We know we're stable. We can nucleate now because all the product in the system is pretty much stabilized. However, we added one more unique thing here is we actually controlled the heat flow, in this case, somewhere around -400 watts per square meter. We did that by dynamically controlling the shelf temperature and making sure that the energy going into the vial was consistent, so we had consistent ice crystal growth post-nucleation. So in this particular application, approximately 9% of the product forms ice crystals during nucleation. Then 91% of it is the ice crystal growth post-nucleation. Just in theory, again, we should have a much more uniform structure, a much more porous structure using this technique. Again, this is top-down initially because of the controlled nucleation. So, quick summary of the different freezing cycles that we've looked at here. The heat flow profile changes dramatically based on the shelf temperature profile and whether you're using controlled nucleation or not. What we want to verify is the assumption that the higher the heat flow creates a smaller ice crystal and therefore a longer primary drying process, and that the more controlled heat flow gives us a more porous structure and hopefully a shorter primary drying cycle. So the next few slides are going to be slides that show the different primary drying cycles. And the key things to look at here is the red line will be the heat flux, the green line will be the measured KV. In the upper right-hand corner, you'll see the freezing profile that was used prior to primary drying. At the bottom of the screen, you'll notice there's a table there that says nucleation was uncontrolled in this case. Post-nucleation, it was uncontrolled. We just basically took it down to -40 at half degrees C per minute. Primary drawing was performed with a shelf temperature of -20 degrees. Again, this is 5% sucrose, 3 mil fill in a 10 mil vial. This particular run took 43 hours, had a KV approximately 10. Product temperature was around -35, and our heat flux was around 150 watts per square meter. Now, you'll notice that the heat flux was fairly stable for the majority, more than the first half of the drawing process. You will also notice that KV started to change around 38% into the cycle. Most people that are doing KV measurements and monitoring will do their measurements between 25 and 30% of the primary drawing process. In this case, that would work pretty well here as well. We could just say it's the KV measurement at that point in time. You'll notice that the heat flow has a fairly smooth transition to the end of primary drawing. It's a very gradual change in heat flow. This is going to be important because we'll notice that that's going to become more dramatic the more porous the structure is. The second freeze-drying primary drawing cycle we ran was during freezing, we held at -5 and then reduced the shelf temperature. In this case, we did have one of those vials nucleate prematurely, so I'm not sure what the total effect was, but in general, we have a pretty flat heat flux line here through probably 60 or 70% of the primary drawing cycle, and the KV is very consistent for the majority of the cycle, up to about 60%. So in this case, it says we used heat flux control for nucleation. That's actually not true. We didn't use heat flux control. We just basically controlled the temperature of the shelf, and we did not use post-nucleation control. So the bottom of that is inaccurate. The shelf control was -20 degrees. This particular run took 41 hours, or about 2 hours less. KV was slightly higher, product temperature about the same, but the heat flow was a little bit higher during the process. So we did have a benefit to holding it at -5 over the prior cycle, which makes sense because in this case, if we held the vials at -5, that means that there was more energy available when nucleation took place, and more of the available ice actually crystallized during the nucleation process. Now, you're going to notice in the next couple slides that KV is going to change, or the measurement of KV is going to change, and we've been bouncing this concept around a little bit. One of the things we've noticed is that when we have heterogeneous nucleation, which I call inconsistent ice crystal structures, or not as porous ice crystal structures, the sublimation front appears to proceed in an orderly fashion from the top toward the bottom. It's not ideal. We have some shrinkage from the sides or maybe the bottom as well, but in general, it's a pretty orderly fashion. So the heat flow stays fairly constant during that, with a slight drop as the cake resistance layer builds up. However, you're going to see when we do a controlled nucleation event and we control the heat flow that the KV is going to be less constant after 30% of the cycle. It's only going to be constant for the first 30%. One of the theories for that, and this is open for discussion, is that maybe as the initial dry layer builds up, because it's a more porous cake, that we start to get channels that start to reach toward the bottom of the vial. And when that happens, we're reducing the surface area at the bottom of the vial and changing the heat transfer characteristics of the system. In this case, we aren't measuring the area at the bottom of the vial, so if that parameter changes, then our KV value would change. We do notice that after about 30% of the cycle, so the first 25% for KV is still very accurate. This also will be affected by the volume of material that you have in your vial. If you have 1 mil in a 10 mil vial, this is going to become less and less meaningful. Okay. So this is the third primary drawing cycle. This is After we did controlled nucleation, we then ramped at half a degree C per minute to -40. You'll notice that we have the freezing cycle on the screen up on the right-hand side there. In this case, at the bottom it says nucleation was uncontrolled, post-nucleation was uncontrolled. I'm sorry, nucleation was controlled, post-nucleation was uncontrolled. Again, we controlled the shelf at -20. We have a dramatic reduction in the primary drying time. In this case, it was 27.5 hours with a higher KV of 12.3. Our product temperature was closer to -36 degrees. And you'll notice that the heat flow at the beginning of the cycle was much higher. I'm showing a line at about 200 watts per square meter, but initially it was almost 300 watts per square meter at the beginning of the cycle. So we obviously have improved the porosity or improved the cake. And there's a sharp line at which the heat flux begins to drop here. And the KV actually was very flat up until about 35% of the cycle. Again, we believe that the area at the bottom of the cake is what's changing, and so the KV starts to change. We will see that we can actually control this in a few slides. The other lines that are on here, by the way, at the very bottom is the green line is the product temperature, so you can get an idea of how stable the product temperature is. The gray and the orange line in the middle, the gray line is the capacitance manometer, the orange line is the Pirani. And for the end of primary drying, we are using the pressure differential between the Pirani and the capacitance manometer because we're not totally sure that our heat flux sensor is under vials that are the last ones to dry. So we use that consistently through each of our cycles. So the fourth method for freezing resulted in the following. We controlled the heat flow post-nucleation. So we controlled the heat flow at about -400. Again, we ran this with the shelf temperature of -20. By the way, these are all run at 60 millitorr, I believe. And in this case, we reduced the cycle time to 24 hours. So we've gone from 43 hours on the initial cycle down to 24 hours. KV was about 12.4, but you'll notice our product temperature is down at -37. So our product temperature is now running much lower. Our heat flux started off up near 300 and maintained up near 225 for the first probably 30% of the run here, so about first 40% of the run. So we have a much higher heat flow going through the process, and we have a lower product temperature. So we've done some significant improvement to the porosity of the cake. And this gives us some ability to actually raise the shelf temperature if we want to during primary drying. So we've gone from 43 hours to 41 hours to 27.5 to 24 hours. Now, we've been controlling the shelf temperature at -20 degrees. We looked at this and said, what if we took this cycle that we just ran, but we controlled the shelf temperature based on the product temperature? In other words, we know what the collapse temperature of sucrose is, and we know that we want to maintain below -34 degrees just to be on the safe side. And so we put those parameters into the system. Actually, let's just review what we've done here. Just really quickly, review. KV increased progressively through each of the different freezing cycles. Primary drying time decreased through each of these cycles. And the temperature of the product continued to get better and better through each of these cycles. And we've actually seen as much as a 5-degree improvement in product temperature in different variations of this. Now, this cycle is kind of novel and unique in that we used the controlled nucleation, controlled heat flow freezing process, but then we controlled the shelf temperature based on the measurement of the product temperature. We attempted to maintain the product temperature at -34, which is 2 degrees below its critical temperature. And in this case, we actually post-nucleation controls at -300 rather than -400. But we controlled the heat flow during the primary drying process. You'll notice that the heat flow changed in a pretty linear fashion. there's a little circle around a blip in the cycle where the heat flow changed, and you can see the kV changed. What that was is we found out after we removed the product from the chamber is that a vial 2 vials away from the heat flux sensor had collapsed because it didn't control nucleate, and it collapsed, and we could actually see that in our measurement. And so that's what that jog in the heat flow is, and the jog in the kV is. But the kV is, if we're controlling the shelf temperature, becomes very stable during the entire process. And you'll notice that at about 540 minutes into the cycle, we had a little jog in the shelf temperature, which raised the heat flux again, and that was caused by the thermocouples coming out of the product. And at that point, the temperature control system actually tried raising the shelf temperature again before it came back down. If it hadn't done that, we think the heat flux would have been very linear downward to the end of primary drying. The most important thing here is that we now reduce the cycle to a 17.3-hour cycle. Again, we've gone from 43 to 41 to 27.5 to 24 to 17.3 hours. The heat flux at the beginning was over 450 watts per square meter, and our product temperature was maintained below minus 34. So a pretty dramatic increase in processing time, or decrease in processing time, increase in heat flow. If we look at the comparison of the 4 different freezing methods, probably should have done this a little earlier, but we'll look at this in review. You can see the light blue heat flux is the initial or normal, I wouldn't say normal, but the more typical freezing cycle. A very low or high heat flux, if you want to call it that, at minus 2,000. That creates a very small crystal structure, gave us the longest freeze-drying cycle, or primary drying cycle. We held at minus 5 and had an improvement in the heat flow, an improvement in the primary drying cycle. The red line in this case was controlled nucleation with a ramp post-nucleation, so we still have that V shape in there. That gave us a 27.5-hour cycle. Then we controlled the ice crystal growth post-nucleation. We reduced it to 24 hours, and because we had an additional boost to the product temperature, we were able to then raise the product temperature, shelf temperature, to a higher level and reduce the cycle time, the primary drying time, all the way down to 17 hours. Fairly significant change. If we compare the primary drying cycles, this is the heat flux during primary drying. We can see that they have different profiles. Actually, the longest one was the bottom one in this case, which is a recipe without the holes. Then we added controlled nucleation, and then the last one, we added the temperature control of the shelf during primary drying. So we get totally different heat transfer profiles during primary drying as well. Conclusions of these 4 tests are that the method of freezing does have a major impact on the heat transfer dynamics. Everybody's been concentrating on the primary drying cycle and how to improve that. This appears to be a pretty interesting tool for creating different crystal structures that would probably be more porous and better for the primary drying cycle. Control of the nucleation and post-nucleation crystal growth produces the lowest product resistance and the most porous cake, which results in the shortest primary drying times. The heat flow during primary drying is less consistent when the ice crystal structures are more porous. That basically is due to, we believe, channels reaching the bottom of the vial and changing the heat flow more dramatically than the normal orderly process that you see with heterogeneous freezing. Control of the product temperature via heat flow control enables significantly shorter processing times, and we're going to be able to show a little bit more of a real-life application for this. Now, again, the comment is that the larger the volume filled, the more important that the freezing process is. If you have a very thin layer of product, the method of freezing is probably less important because the cake becomes very porous very quickly, I guess is the best way to put it. Now, everything that we're talking about here, heat flux is still in its infancy. There's a lot of improvement to be made to the process and to the measurements, but we're seeing some pretty favorable results so far as to identifying what a better freezing profile is and how that affects the primary drying cycle. We've recently had the opportunity to perform some testing on a protein cycle, a live protein, or a real protein, I should say. That protein had sugars and buffering salts in it, had a solid content of 21 milligrams per milliliter. It was a 21 milliliter fill in a 50 milliliter tubular vial. T-critical was originally considered to be somewhere between minus 24 and minus 27, depending on how it was frozen. Key point there is how it was frozen. The original cycle that was developed with an annealing step, and it took a total of 121 hours from start to finish. 18 of those hours were freezing with annealing, 92 hours in primary drying. That was with a T-shelf of minus 5, a vacuum of 70 millitorr, and then a secondary priming process of about 11 hours. We took that product and looked at a couple different cycles, but I'm going to really jump to the end where we did controlled nucleation with controlled heat flow, and we controlled the product temperature during the primary drying cycle, and we'll see what the results were on that. So here's the actual freezing cycle. That previously, I think, was 18 hours. Here again, you can see that we went to minus 5 degrees on the shelf, allowed that to stabilize, did our nucleation event, which is that sharp drop in the heat flow all the way down to about minus 650 watts per square meter. Then we controlled the heat flow at about minus 600 watts per square meter until everything had crystallized and the maximal freeze concentrate had solidified, and the heat flow came up to approximately 0. So that process there was shortened quite dramatically using controlled nucleation and controlled heat flow. It's about a third of what it was. We then popped that into the freeze dryer and ran a cycle. We limited the shelf temperature in this particular case to plus 10 degrees just as a safety factor. So initially the shelf temperature went up to about plus 10, came down to about minus 1 at one point. At that point, some of the thermocouples had come out of the material, so we disabled those thermocouples. It allowed the shelf temperature to stabilize at about plus 1. It was about plus 0.08, plus 0.8 degrees actually, for the remainder of the cycle, and still maintaining our product temperature below minus 29 degrees. So we used a critical temperature of minus 27. We wanted to control at minus 29 or lower for the product temperature. You'll notice that with controlled nucleation, controlled heat flow, and then controlling the product temperature, our primary drying cycle was now 37 hours versus the 92 hours initially. KV in this case was about 12.5, and our heat flow stayed somewhere it was up in the 400 range initially, and then slowly came down throughout the process. KV was pretty consistent. The yellow line there is KV. It looks like KV was consistent up through about 60 to 70% of the process in this case, because we are controlling the shelf temperature. Once the thermocouples start coming out of the product, it makes it difficult to actually measure KV. So that's the point at which we stopped measuring it, or we stopped using that. The secondary drying cycle, we didn't change that at all. We left it the same way, as ramp it up to plus 30, I think it was, and then hold it for several hours, for 6 hours. You'll notice that the heat flow initially went up and then drops down, and so we can tell by the heat flow if we're pretty dry in this case, the 6 hours of secondary drying looks like it worked pretty well. You'll notice that the Pirani is the blue line at the top in this case, and that came down and met the capacitance manometer pretty nicely toward the end as well. So comments on this cycle is, in this case, less than 7.5% of the water crystallized during controlled nucleation. So the larger the mass of water, in this case the mass of water to the mass of vial, the mass of vial was lower than from a ratio perspective, and so only 7.5% could actually nucleate. Probably less than that nucleated because our entire vial is not at -5 when it nucleates. So 92% or more of the crystal growth takes place post-nucleation. All the vials did nucleate in this particular application. During primary drying, we used the capacitance manometer versus the Pirani. So that ended up being a 37-hour cycle. We measured the KV at 12.5, and the cake did not appear to have shrunk during the primary drying. It was a very acceptable appearance, and so if we look at the end result on that, our total elapsed time with the new cycle was 54 hours, so we took it down from 121 to 54 hours. It ran at 45% of the original cycle, or we reduced it 55% in time. The cake structure was still visually acceptable. The initial residual moisture tests that were done were 0.61% plus or minus 0.04%, which are very tight. So it looks like in practical application, it looked like it worked extremely well for this particular application. Obviously, by being able to reduce your cycle times by more than 50%, could have a dramatic impact on your throughput. You could buy a smaller freeze dryer or double your throughput either way. A little bit about where this is going in the future, because there's a lot of work that still has to be done. We're taking the same technology and putting it into what we call a micro freeze dryer. This is basically a 6-inch diameter shelf. It's going to have the heat flow sensor mounted in the shelf. There'll be a heat flow sensor mounted on the irradiant plate above the material, and there'll be a heat flow sensor mounted on the wall as well. In this case, the wall will be able to be temperature controlled to simulate different situations and hopefully different size systems. You could simulate edge vial effects and things like that. The idea with this is to hopefully develop a system that will enable developing protocols with much less material and then being able to scale that up into different machines. So the micro FD is in prototype right now. We're actually starting to use that as we speak. It also has the capability of doing controlled nucleation, so we can test the different freezing methods against each other. Hopefully this will be a nice tool for future users. In addition, one of the key parameters for transferring protocols is KV. If we know the KV of similar applications in different machines, we can simply go back and control the heat flow at the same level change the shelf temperature to accommodate the same KV. This should be totally feasible in the future. It's something that we're working on. And once you have run a conditional run of your product and know what your KVs are, it's a simple transfer of shelf temperature. Hopefully that will be something that people will be working on in the near future with their existing equipment. So in conclusion, freezing and ice crystal formation is a critical factor in producing a robust and efficient freeze-drying process. Heat flow monitoring and control can give you more insight into your crystal formation, into what's happening during the process. If in some processes your cake shrinks significantly, you can watch what's going on there and get a better feel for how to control the cycle. Controlled nucleation and controlled heat flow does dramatically improve the crystal structure for the primary drying process, and it allows higher shelf temperatures and shorter primary drying times. KV should be measured in the first 25 to 30% of the primary drying cycle, even when controlled nucleation is used. After that, the systems seem to become pretty dynamic. These systems really shouldn't be modeled as steady state. They really are dynamic. Sublimation for porous structures proceeds differently than for heterogeneously nucleated product. Like to find out more about that. We haven't studied that. Maybe some people out in the field will be doing that. It doesn't appear that the sublimation front proceeds in an orderly fashion. There's work to be done on bulk systems and things like that as well. Let's see here. Okay, we're toward the end. There's a lot more to talk about, but we'll probably best to open up the floor to discussions and questions and answers, and then that'll bring up some other topics that we can get into.
Okay, perfect. Thank you, Mr. Thompson. So yeah, like we said, we'll begin the question and answer portion of the webinar. We had a lot of great questions coming in during the presentation. So our first question: this fog technique, is it the same as Verisec?
No, there are basically three major techniques out in the marketplace. The first technique was developed by Praxair, which uses a depressurization technique. They fill the chamber to 2 atmospheres with argon or some other material, nitrogen or something, and release that pressure. That requires an ASME-coated vessel to do that, so it works on steam sterilizable systems, but it doesn't work on laboratory systems. The Verisec unit uses liquid nitrogen, and they spray in a mist of water into the liquid nitrogen stream and flow that through the chamber to create the nucleation effect. It's a longer process than freeze booster. What freeze booster does is we build up an external seeding. We reduce the pressure of the product chamber somewhere down to 50 torr, not 50 millitorr, 50 torr, and then open an isolation valve and draw in the ice crystals into the chamber through the differential in pressure and seed the product. We've demonstrated that on systems up to 100 square feet. For production 200 square feet and higher is probably not the way to go, but for the laboratory, it's a fantastic tool. You can just retrofit it right to the system.
Okay. We have another question. Did you use the freeze booster to control nucleation for the freeze drying of the protein product?
Yes. Yep. The protein product was done identical to the way we were doing the sucrose. We used freeze booster and controlled nucleation, freeze booster controlled nucleation and controlled heat flow, the same as we did for the prior runs.
All right. And then follow up: is Millrock technology P80 controlled lyophilization commercially available? Yes.
Yep. We sell it on our equipment. It's also available in a standalone mode. If you have an existing freeze dryer and you'd like to add the controlled nucleation, you can get a nucleation station to add to your system, and we would do a standalone heat flux system, or what we call AccuFlux. The only thing with that is you wouldn't be able to feed it back to your existing control system for controlling the shelf temperature during primary drying or even post-nucleation. I'm sure that some control systems we could probably work with better than others. But what we would do is we would supply that. If you wanted something on an existing freeze dryer, first start with a standalone system so you can get data on it, and then figure out a way to actually incorporate that into the control of the shelf temperature.
Okay. We have another question that came in. Can the controlled nucleation be retrofitted to other commercial scale lyos?
Yeah, when you say commercial scale, in this case, again, we're really comfortable up to 100 square feet with freeze booster controlled nucleation. Over that, it's a pretty big deal. Unfortunately, that's true of all of the controlled nucleation methodologies. Our sweet spot is really in the laboratory, where you might have a 1 square meter, 2 square meter system that'd be 10 to 20 square feet. 30 square feet, it works extremely well as well. 100 square feet, you start to get into the commercial sizes and larger, and it's probably not. It's feasible to do, but we're really more comfortable below 100 square feet.
Okay. How pure is the product, and as a follow-up, can we co-crystallize?
Need more information on it. When you say how pure is how pure is the product?
Yeah, the question was written, how pure is the product, and can we co-crystallize? We can, that can be a follow-up question for after the webinar.
Yeah, if I'm not sure what co-crystallizing means. If they're referring to controlled nucleation and our freeze booster technology, we use WFI as the seeding material, so it's pure. Co-crystallizing would mean if you want to mix it with something else. Yeah, I guess you could. We have, I can't talk about another patent that we have on improving this, but yeah, that's a feasibility.
Okay. We have another question. Do you run samples for customers, and can you handle anti-cancer compounds?
We can run projects for people. We don't have a what I'll call a clean lab. We have a industrial freeze dryer lab. We really can't handle cytotoxics and things like that. If you're working with somebody in the field now that's doing that work for you, we'd be willing to work with them to get it into their system so you could try it.
Okay. Another question we have that came in, is there a relationship between heat flux measurements and residual moisture in products?
Yes, but I don't know what it is. In this particular case, with the protein run that we did, we could see that the heat flux after secondary drying had reached stability and wasn't going to get any lower. So we knew that it basically wasn't going to get any drier than it was. And it ended up being 0.61%. We haven't tried controlling that, and we haven't done any real qualitative studies on it. So, but we can see that the heat flow has stopped and leveled off, and that further secondary drying is just not going to give you any better result.
And what's the nominal freezing rate for a liposomal product? The person who's asking the question understands it should be fast freezing, and they want to know, does annealing help? They expressed there's some concerns about aggregation and size increase. Yeah, there's always a complication with freezing. First off, we used to simplify freezing really poorly, and then we realized that some products actually have to be frozen quicker rather than slower. In this case, we were trying to maximize the pore size and control the crystal growth for a larger crystal. You can also do that for a faster freeze. Now, the limit would be the performance of the equipment. We've actually had to make systems that could cool the shelf at 20 degrees C per minute, for example, because you get aggregation or different issues with proteins if you don't freeze them properly. It's pretty specific to each product, though, and I'm not sure I'm answering the question totally, but I think that's as much as I can go for it. I'd be happy to look at it after this as well. Okay. Do you see any value in using controlled heat flow without using controlled nucleation in a cycle? We didn't run that test. I had run that originally and found that the nucleation was still so heterogeneous that it was almost impossible to control. So what we're going to do next is we're going to go back and look at the method of control. And I'll just explain it very quickly. Is if we're trying to control, let's say, at 300 watts per square meter or minus 300 watts per square meter, and you have a nucleation event near the sensor, that might drop down to minus 600.
Well, that's only the vials that are near the sensor. Other vials are still not nucleated. We don't want to raise the temperature of the shelf to control at minus 300. So it's going to take a little bit of thought on what to do there. Typically, we'd be running at much lower or much higher heat flows, basically. If you wanted to control it at minus 600 or something like that, it might be feasible. But it is something that we want to look at.
Okay. We had a couple questions asking about a little bit more about information about your LyoPat software capabilities. And
Yep.
One specific question, does your lyophilizer software calculate mass flow?
Yes. We calculate, in fact, let's take a look at that really quickly here. This is a sample of the screen that would be used for entering data. I don't expect anybody to absorb this, but I can tell you, if you look under control options in the middle of the screen there, you have the ability to run this with or without thermocouples, with or without nucleation, with a freezing recipe, or using heat flow for freezing, with a drying recipe, or using the temperature of the product for primary drying, or any combination of those. You put in your critical parameters, and the software takes care of that for you. So that's how we were very easily able to compare different methods of different freezing versus primary drying methods. So that's all built into the software now. This following page here shows some of the information that we display. In fact, this is kind of interesting. It's going to get me off on a little tangent, so it'll be about 2 minutes of tangent. If you look on the left-hand side, there's some of the data that we get. We get the percent. If you look on the, it constantly measures the surface temperature at different sensors, the heat flux at different sensors, the temperature average. You can group your thermocouples into groups near each sensor, and actually use that for the local KV. You'll notice the KV in this particular one is all over the place because the thermocouples are out of the product, so the KV is meaningless. But this is some of the saved data. During freezing, we actually calculate the amount that would be frozen by nucleation. We calculate the energy or measure the energy that was taken out during each of the freezing steps. And then during primary drying, we calculate the mass flow per vial, the mass flow for the batch, the mass removed. Obviously, we know the total mass. We calculate the percent dried. You'll notice in this case it was 98%, 97%, 99% essentially of the measurements. They're not always that close because we're looking at local events that take place, and they're not always the same. We also measure the cake resistance in torr square centimeter hour per gram. And these are all, by the way, all this data is saved and can be graphed and reviewed. We estimate the primary drying time, but I'm going to be right up front and say our calculation there is terrible, that we've got to improve. Now, the interesting part of this screen is if you look at the right-hand side where that arrow is pointing, if you're running a recipe, at the end of each step of the recipe, we will take a snapshot of the product temperature, surface temperature, shelf temperature, KV, cake resistance, mass flow, pressure, percent dry, and the heat flux at each step. And this is really a neat tool for those of you that are interested in doing something like a design space. Because what you can do in a recipe is you could say, all right, I want to run my shelf temperature at -5, and I want to see what happens when I change the vacuum level. I want to see what happens to KV and my mass flow. And so in step 1, you can put -5 and 50 millitorr. In step 2, you can put in -5 and 100 millitorr. In step 3, you can put in -5 and 150 millitorr, and that'll save snapshots of it, and you can look at that and compare them. Then you can go and say, oh, wait, let me see what happens when I change my shelf temperature. So step 4, you would say, go to 0 degrees C, hold it, and 50 millitorr. 0 degrees C, 100 millitorr. 0 degrees C, 150 millitorr. And you can actually create a design space by doing this, where you can then take this information out and map it. kind of a powerful tool. So if we take a look at some of the information that we do get out of the system, here are some of the things that we can actually see and monitor. Because of the heat flow, we can actually see the end of the supercooling and the freezing. We can watch the energy for nucleation and crystal growth and things like that. During primary drying, we have KV, cake resistance, product temperature, heat flow, mass flow, total heat removed, mass flow per vial, percent dried, end of primary drying, and a secondary drying if you really wanted to. And this is all available through the software. So the long answer to the question is yes.
Great. Thank you for that. So unfortunately, that is all the time we have today. Any questions that we were not able to address here live will be answered by our presenter via email. So I'd like to thank Mr. Thompson for sharing his knowledge with us, and also offer a special thank you to Millrock Technology for sponsoring today's event. Please keep a lookout for an email containing a link to view this webinar on demand. Thank you very much, everyone.
Thank you all.